Next, consider the cyclic group Zn. Every subgroup of Zn is cyclic. To each positive divisor, K of n, there is exactly one subgroup of Zn of order k generated by n by k. A small illustration. Consider Z18. 0, 1, 2, 3, so on till 17. Now here, positive divisors of Z18 are 1, 2, 3, 6, 9, 18. The subgroups of Z18. So basically, these positive divisors are order of these subgroups of Z18. So order 1. It will contain only one element and it will generate the whole Z18. Order 2. Basically, in from these elements I am writing those elements which have order 1. Now order 2, 0 and 9. Order 3, 0, 6, 12. Order 6, 0, 3, 6, 9, 12, 15. Order 9, 0, 2, 4, 6, 8, 10, 12, 14, 16. Generator 2. Order 18. Next is an important concept. How to find number of subgroups of Zn. This is equal to number of positive divisors of n. To count the number of positive divisors, of n belongs to Z plus, have the number theoretic function. Number theoretic function is a function whose domain is Z plus. means set of positive integers called the tau function. So how to find this? For n belongs to z plus, tau n is the number of positive divisors of n. If we are writing n in the form of prime factorization, p1 to the power a1, p2 to the power a2, so on till pn to the power an, then tau n is simply a1 plus 1 into a2 plus 1, so on till an plus 1. सिंपली ये जितनी भी पावर्स हैं उसमें 1 ऐड करके मल्टीप्लाई कर देंगे. फॉर एग्जाम्पल, find the number of subgroups of Z30. So n is 30. Prime factorization will be 2 into 3 into 5. So tau n, tau 30 is simply 1 plus 1 into 1 plus 1 into 1 plus 1. 2 into 2 into 2. 8. Therefore, there are 8 subgroups of Z30. Next, we can count the number of elements of each order in a finite cyclic group. Means in a finite cyclic group we can find number of elements of each order. Define a number theoretic function called the Euler phi function it is denoted by phi n such that phi 1 is equals to 1, phi n for n greater than 1 is the number of positive integers less than n and relatively prime to n. Phi n is equals to order of un. Therefore, if G is a finite cyclic group of order n and D divides n, means its divisors divides n, then number of elements of order D in G is phi d, and summation phi d, d divides n is equals to order of group G. Now some results for Euler phi function. If p is a prime number, then first phi p is equals to p minus 1, means 2 is a prime number, phi 2 is simply 1, 3 is a prime number, phi 3 is 3 minus 1, 2. Phi p to the power n, this is p to the power n minus p to the power n minus 1, where n belongs to natural numbers. Third, phi p dash q, this is phi p dash into phi q, provided GCD of p dash and q is 1. Some more important results for cyclic group. First, if order of A is equals to n, then order of A to the power k, this is equal to n upon GCD of n comma k. Second, every subgroup of a cyclic group is cyclic. But the converse need not be true. That is, if every proper subgroup of a group is cyclic, then it is not true that a group is cyclic. For example, U8. If I take any subgroup of this U8, then it will be cyclic, but U8 itself is not cyclic, because we have discussed yesterday that we were not getting any element whose order is equal to the order of the group. Its order was 4. Every group of prime order is cyclic. If order of G is equals to P, P is prime, then G is cyclic. Next, if order of G is equals to PQ, where P and Q are primes such that P is less than Q and P does not divide Q minus 1, then G is cyclic. For example, let order of group G be 15. It can be written as 3 into 5. Here P is 3, Q is 5. Both are prime numbers. P is less than Q. Now let us check whether P does not divide Q minus 1 or not. 3 does not divide 4. So Any group of order 15 is cyclic. Let G be a finite group of order n. Then number of cyclic subgroups of G of order D is equals to number of elements of order D in G divided by phi D. Next, infinite group has an infinite number of subgroups. Result, let G be a group. G is finite if and only if it has a finite number of subgroups. Next, the set of real numbers under usual addition is not cyclic. Can you tell me why it is not cyclic?
It may not be follow commutative property.
Commutative property.
Sorry. एडिशन है ना वैसे भी ठीक है
साइक्लिक क्यों नहीं है
बता साइक्लिक का मतलब ये हुआ ना कि वो जनरेट करेगा सारे एलिमेंट्स को एक एलिमेंट तो यहाँ पे अगर मैं जीरो लूं तो जीरो तो नहीं जनरेट करेगा ना सारे एलिमेंट्स को 0+0 0 0 वो सारे ही जीरो ही होंगे ना
order of 0 is 1 and every non-identity element has infinite order. So it will be not cyclic because all the elements of this will not be generated. Next, the set of non-zero real numbers R star under multiplication is not cyclic. R star under multiplication. Order of 1 will be 1, order of -1 will be 2, and remaining elements has infinite order. The set of positive rational number under multiplication is not cyclic. Question: the number of generators of the additive group Z36 is equal to
नाइन आएगा इसका आंसर. अच्छा 9 तो है.
ऑप्शन में ही नहीं. निकालेंगे कैसे? Number of generators of a cyclic group G
तो अगर डिवाइजर से लें वैसे 36 का तो भी डिवाइजर है, 3 भी है.
This is calculated by phi n.
हाँ.
This is Zn ना, Zn with respect to addition modulo n is cyclic group. So phi 36. So n is 36. Prime factorization of 36. Two square into 3 square. Now phi 36 is formula एक और बताना था इसमें. If n is equals to p1 to the power alpha 1, p2 to the power alpha 2, so on till pn to the power alpha n.
इसका आंसर है.
इसका आंसर निकाला नहीं मैंने, निकाल लेते हैं. n इंटू 1 minus 1 upon p1, 1 minus 1 upon p2, so on till 1 minus 1 upon pn. Phi 36 is 36 into 1 minus 1 upon 2, 1 minus 1 upon 3. 2 by 3. 12.
Yes, ma'am, 12 आ रहा है.
B part. The value of alpha for which g is equals to alpha 1, 3, 9, 19, 27 is a cyclic group under multiplication modulo 56. A part 5, B part 15, C part 25, D part 35.
है. 25.
Yes. How you have done this?
By using the property of generator ना, cyclic group है ना, तो multiplication module है. So if I multiply 1, है ना, so it n number of times, it will give 1 only. Then 3 into 3 into 3, 81. So 27 will be less, na? So if I 81 में से 56
Basically
minus
generator of
तो
3.
25 आएगा.
3, 9,
47, 81.
81 minus 56.
25 आएगा.
25.
Similarly 9 का लिया, 9 का स्क्वायर 81, अगेन 25 आएगा.
9 का स्क्वायर
9 into 9 ना, जनरेटर ही है ना.
नहीं, एक ही जनरेटर देख लो, उसी से पता चल जाएगा कि एक
अच्छा.
और ये एलिमेंट क्या होना चाहिए. तो इसमें से कौन सा वाला मिसिंग है? 25 मिसिंग था.
ठीक.
If Zg denotes the center of a group G, Then the order of the quotient group, G by ZG cannot be A part 4, 6, 15, 25.
Four. First option. नहीं. Just a minute. इसमें बी ऑप्शन रहेगा 6.
नहीं,
फिर नहीं आ रहा मुझे, कैसे करेंगे इसको?
बताती हूँ. We will use the result that if G by ZG is cyclic, then G is abelian. Therefore, if order of G by ZG is 4, is every group of order 4 is cyclic? Every group of order 4.
मेरे ख्याल से नहीं होता शायद. इसमें कोई वो A4 का कोई कंसेप्ट है ना इसमें, ऑल्टरनेटिंग ग्रुप वाला.
A4 का ऑर्डर तो 12 नहीं होता?
याद नहीं आ. आप बता, क्लियर याद नहीं आ रहा मुझे कंसेप्ट इसका.
इसमें एक ऐसा ग्रुप है, क्लीन्स 4 ग्रुप याद है?
नाम तो सुना है, क्लीन 4 ग्रुप,
जिसके अंदर x, y such that x square equal to y square equal to identity. xy का square equal to identity. So this is the smallest non-cyclic group. ठीक है, आपके सामने है
हम्म
K4 है, तो इसका ऑर्डर तो 4 है ग्रुप का खुद का, ऑर्डर ऑफ K4 इज 4, बट इन दिस एवरी एलिमेंट हैज ऑर्डर 2 ना, x स्क्वायर इक्वल टू आइडेंटिटी, y स्क्वायर इक्वल टू आइडेंटिटी, order of x is 2, order of y is 2, so every element in this has order 2, there does not exist any element of order 4. साइक्लिक होने के लिए तो कम से कम एक एलिमेंट का ऑर्डर ग्रुप के ऑर्डर के इक्वल आना पड़ता है, तो ये तो साइक्लिक को ऐसा जरूरी ही नहीं है, तो इसको तो हम वैसे ही डिस्कार्ड कर सकते हैं। मतलब ये पॉसिबल है कि ऑर्डर ऑफ g अपॉन जेड जी 4 हो जाए। सिमिलरली b के लिए भी सेम लॉजिक, बट c के लिए g अपॉन जेड जी 15, अभी मैंने ऊपर करके दिखाया था, एनी ग्रुप ऑफ ऑर्डर 15 इज साइक्लिक, ये रहा। So if it is cyclic, then G is abelian by this result. So this implies G upon Zg is cyclic because every group of order 15 is cyclic. This implies that G is abelian, and we have discussed that if G is abelian, then G is equals to center of group na, because Zg is center of group and it is abelian. So if G equal to Zg, then order of G upon Zg will be 1. Is this clear? It will be 1 na, which is a contradiction because we have taken in the starting that it is 15, which is not possible. So answer will be option C. मीन्स कहीं पे भी आपका ऑर्डर ऑफ जी बाई जेड जी लास्ट में जाके ये 1 बन जाए ना, तो ये पॉसिबल नहीं होगा, कॉन्ट्रडिक्शन आ जाएगी।
बस हमें तो ये बताना है ना, कैन नॉट बी।
तो ये पॉसिबल नहीं है ना 15 वाला लेके, कॉन्ट्रडिक्शन आ रही है ना 15 वाला लेके। ऑर्डर 6 वाला भी जरूरी नहीं है साइक्लिक हो, एक बताती हूँ एग्जाम्पल इसका भी। अभी वैसे मैंने डायरेक्ट प्रोडक्ट बताया नहीं है, जैसे ऑर्डर 6 का नॉन साइक्लिक ग्रुप देखना हो, नॉन साइक्लिक एस, सॉरी सिमेट्रिक ग्रुप नहीं बताया ना मैंने अभी, S3, ऑर्डर ऑफ सिमेट्रिक ग्रुप इज n फैक्टोरियल ना, so order of S3 is 3 factorial. This is a non-cyclic group. बाकी अभी कंसेप्ट्स आगे बताऊंगी तो और रिलेट कर पाओगे कि कैसे हो रहा है, क्योंकि एग्जांपल्स पता होने इसमें ज़रूरी है। नेक्स्ट इज डायहेड्रल ग्रुप्स। पहले अब वही हम पढ़ने वाले हैं, दो टाइप के Non-abelian groups. Two very important. Non-abelian groups. First one is dihedral groups. Second one is symmetric groups. Dihedral groups. So what do you understand by a polygon? A polygon is a closed plane figure
made by line segments.
That is made up of finite number of straight line segments. Regular polygon. A regular polygon is a polygon which is equiangular and equilateral. For example, equilateral triangle, it's all the angles are equal and sides are also same. Square, regular pentagon, etc. Next, simple polygon. A simple polygon is a regular polygon that does not intersect itself. Regular n-gon. It has n number of sides. A regular polygon with n number of sides. Next, symmetry of a regular polygon. Symmetry of a regular polygon is the rotation, angle of symmetry and reflection. Which is called line of symmetry. Of the polygon by which if the polygon is rotated or reflected, gives the original figure except for the labels. So first is symmetries of a square. One, two, three, four. So this is our original figure. Rotation by 0 degree. It will remain same. One, two, three, four. Next, rotation by 90 degree. And it will be rotated in this direction. So R0 is given 1, 2, 3, 4. So on rotation we will get R90 as 1, 2, 3, 4. Next, rotation by 180 degree. So we had this R0 1, 2, 3, 4. So it will be basically shifted 2 places. So this will become 1, 2, 3, 4. This is R180. Next, rotation by 270. One, two, three, 4. Now it will be one will be shifted 3 places. So it will become 1, 2, 3, 4. R270. So a square has 4 rotational symmetry. Because rotation by 360, then we will get the same figure, the original figure. So there are 4 rotational symmetry. Next, reflection. R0 is this 1, 2, 3, 4. Reflection by horizontal line. So this will become 1, 4, 2, 3. So this is reflection by horizontal line. Next, reflection by vertical line. One, 2, 3, 4. is capital V. Next, reflection by main diagonal. So this will become capital D. Reflection by other diagonal. D dash. So a square has four reflectional symmetry. Consider a rotation of R0 by 90 degree followed by a reflection by the main diagonal. So original figure is this 1, 2, 3, 4 R0. So R90. 1, 2, 3, 4. This is R90. Now by main diagonal. So this will be 1, 4, 3, 2. One, 4, 2, 3. एक minute. This is B. Now some remarks. First, a rotation followed by a rotation is a rotation. Second, a reflection followed by a reflection is a rotation. A reflection or rotation followed by a rotation or reflection is a reflection. So what is a dihedral group? The dihedral group denoted by Dn under function composition is a group that consists of all the rotational and reflectional symmetries of regular n-gon. Order of Dn is 2n. It will have n rotations and n reflections. It can be written as Dn is equals to r comma s such that r, one second, r to the power n is equals to s square is equals to identity, rs is equals to sr inverse. This is also called the group of symmetries of a regular n-gon. Now Cayley is table for D4. R0, R90, R180, R270, H, B, D, D dash. R0, R90, R180, R270, H, B, D, D dash. So this will become R0, R90, R180, R270, H, V, D, D dash. So R90 composed with R90. We will get R180. R90 composed with R180, R270, R0, D dash, D, H, V, D dash, D. I am doing this by the similar manner I have shown this one. Rotation of R90 by R90. followed by a reflection of the main diagonal. R0, R180, R90, R270. Next, properties of the dihedral group are important. First, D4 is R, S such that D4, यहाँ पे भी अगर यहाँ DN लिखा है ठीक है, so D4 R to the power 4 equal to S square equal to identity, RS is equals to SR inverse. R0 is R identity, R90 is first rotation, R180 R square, R270 R cube, H is V is R square, also inverses. Inverse of R0 is R0, R90 R270. Inverse of R90 is R270 and inverse of R270 is R90. मतलब ये आप करके भी देख सकते हो, सिंपल जो आपकी इन्वर्स की डेफिनेशन है, A V equal to identity. So this means that R90 composed with R270 should be R0. Means except R90 and R270, all the elements of D4 are self-inverses. So this is E R R square R cube, S SR square SR SR cube. Second, order of each reflection is 2. R is equals to rotation by the angle of (360° by n for an n-gon order of R is 360° upon n. This is important. Center of dihedral group. When n is even, then it will contain R0, R180°. And when n is odd, then it will only contain R0, means original figure. The subgroup of rotations form a cyclic group in Dn. Cyclic subgroup in Dn. Subgroup of rotations E, R, R square, R cube, so on till R to the power n minus 1. Next, this is also important. Number of elements of order 2 in Dn. N when n is odd. When n is even, then n plus 1. Next, let Dn be a dihedral group and D be a positive divisor of n. Such that D is not equal to 2. The number of elements of order D in Dn is equal to phi D. For example, order of D6 is, order of Dn was 2n. So order of D6 will be 2 into 6, 12. So it will have 6 rotations and 6 reflections. Divisors of 6 are 1, 2, 3, 6. So number of elements. When n is odd, number of elements of order 2. When n is odd, then n. Here n is 6. Number of elements, 1 minute. Number of elements of order 1 in D6. Phi 1. 1. And number of elements of order 2 in Dn. When n is even. 6 plus 1, 7. Number of elements of order 3. Phi 3. 3 is a prime number. So phi p was p minus 1. So 2. 6. So 6 के लिए phi 6 will be 6 can be written as 2 into 3. 6 into 1 minus 1 by 2, 1 minus 1 by 3. 6 into 1 by 2, 2 by 3. 2. Next, total number of subgroups in Dn. Number of divisors of n. Plus sum of divisors. For example, number of subgroups in D6. Number of divisors of 6 are 4 plus sum of divisors 1 plus 2 3, 3 plus 3 6, 6 plus 6 12. So there are 16 subgroups in D6. Next illustration. Number of cyclic subgroups in D6. Number of cyclic subgroup of order D is calculated by the formula
Two.
2
नहीं टॉसिक से
नहीं, number of elements of order d upon phi d.
हाँ
So number of cyclic subgroup of order 1. ऑर्डर 1 का तो 1 ही होगा. नंबर ऑफ साइक्लिक सबग्रुप ऑफ ऑर्डर 2. ऑर्डर 2 का भी हमने यहाँ पे देखा था 7 आया था. 7 upon phi 2. 7 because phi 2 is 1. Number of cyclic subgroup of order 3. Number of elements of order 3 were 2 upon phi 3. Phi 3 is also 2. 1. Number of cyclic subgroup of order 6. Number of elements of order 6 were 2 upon phi 6. Phi 6 was also 2. 2 by 2, 1. Therefore, total number of cyclic subgroups of D6 is 1 plus 7 8 plus 1 9 plus 1 10. So after this we will continue in the next class. Next topic will be symmetric groups.